Today we are going to be talking about instantaneous power and average power in steady state sinusoidal circuits. Make sure I'm spelling things right. All right, so let's consider a fairly simple system where we have some time varying voltage source, Vs of t, that is supplying power to some generic circuit element where there is some voltage drop V of t across the terminals of our generic circuit element, and there is some current I of t flowing through our generic circuit element. I would like to explicitly state that Vs of t, which we could obviously see is going to be equal to V of t through Kirchhoff's voltage law, will be of the form Vm cosine omega t plus theta v volts. So it's just a simple sinusoid having a particular magnitude, excitation, frequency, and phase angle. And we should expect that our current I of t will have a similar form. Im cosine omega t plus theta I. So if we wanted to determine the power absorbed by this generic circuit element, what would we do? This is a first day of circuits 1 question. Yeah, P is equal to IV. So the power absorbed, the power as a function of time absorbed by our generic circuit element will be the voltage V of t multiplied by the current I of t. So that is going to look like Vm cosine omega t plus theta v multiplied by Im cosine omega t plus theta I. And that would be Vm Im cosine omega t plus theta v times cosine omega t plus theta I. So what happens when we multiply 2 cosines together? Anybody remember trig identities? If you don't, it's okay, I do. So what we have here, let me do it in blue, is, I meant to do it in blue. Cosine phi1 times cosine phi2. Okay, so just 2 different angles where phi1 represents omega t plus theta v, because that's all just for a given point of time, that's just an angle, right? Omega times time is giving us an angle to which we are adding a phase angle. So I can represent all of that as phi1, and then omega t plus theta I then becomes phi2. So when I multiply 2 cosine functions together, like this, what I'll find is I have 1/2 cosine of phi1 minus phi2 plus 1/2 cosine phi1 plus phi2. That's our trig identity that we're going to be using here. So I'm going to have a 1/2 out front. Obviously, I'm scaling this identity that I'm using by a factor of Vm times Im because there's a constant out in front. So that constant would just be applied to both portions. So I'll have 1/2 Vm Im, bless you, cosine. So when we have omega t plus theta v, that quantity, minus omega t plus theta I, all that's left is just theta v minus theta I, right? The omega t's cancel each other out. And then we're going to have a second term, 1/2 Vm Im cosine. Now we add those two angles together. So we're going to have twice omega t plus theta v plus theta I. Excuse me. So this is our expression for the power being absorbed by a generic circuit element. It is valid for resistors, capacitors, inductors, sources, all that kind of stuff. Valid for everything. If we were to plot this, it would look something like this, depending on what the circuit element is. I'm going to say it's a generic circuit element having some resistance and some inductance, okay? So what, excuse me, what we would observe, actually let me, is that we would have an oscillating power signal. Trying to draw a sinusoid as best I can. So we'd have an oscillating power signal like so that could potentially dip below our horizontal axis here, okay? Just depending on the ratio of the component values and all that kind of good stuff. This particular power waveform would be oscillating at twice the frequency of our voltage and current waveforms. And it has an offset value. So it's not centered around the horizontal axis. Instead, it is offset by some specific amount. Well, the offset is this term right here. Right? I'm calling it a DC offset because it's a constant value of power. But what it really represents is the average amount of power that's being supplied, or excuse me, being absorbed by this generic element. So I'm going to call this P average, okay? Because that's the average value of the sinusoid. Half the time the sinusoidal part is above that DC offset value, and exactly half the time it's below that DC offset value. Then this big part right here represents a superimposed twice omega AC signal, right? Operating at twice our angular frequency over voltage and current. All right, so what do these portions where our instantaneous power signal dips below the horizontal axis represent? So what does it mean on a graph when you go below the horizontal axis? It's negative, okay? So if this graph is representative of the power absorbed by our element, then yes, that means that over those very small intervals, our generic element here is supplying power back to our system. We will observe that that happens anytime we have capacitors and inductors in our circuit, because we know that they are temporary energy storage elements. What we'll find out momentarily is that exactly half of the time a capacitor and an inductor absorbs power, and exactly half of the time a capacitor or inductor supplies power. All right. So let's talk about what would happen specifically with a resistor. All right, so let's say that our power is being absorbed by a resistor having a value of R. And we are obeying the passive sign convention where the current is flowing into the positive polarity terminal. Do you guys remember what the relationship between the phase angles for the current and voltage in a resistor are?
The current leading.
For a resistor, no.
Oh.
Resistor, the phase angles are identical, right? We know that theta V must be exactly equal to theta I. Similarly, we know that Vm is equal to Im times R. And we know that Im is equal to Vm over R, right? That's just Ohm's law, nothing wild or crazy there. So we can use these relationships and say that the power absorbed by a resistor, so let's call it PR as a function of time. So let's see. We could have 1/2. So Vm times Im, that could either be, we're going to wind up with two different representations, so I'll write them both kind of simultaneously. So Vm times Im could either be Vm squared over R or Im squared times R, based on me just multiplying those two representations for Vm and Im that we talked about up there. Then I'm going to have cosine of theta V minus theta I, right? So what is theta V minus theta I for a resistor? Bless you. Yeah, so theta V minus theta I must be 0. So cosine of that is equal to 1. So that first term just looks like 1 And then we're gonna have that same 1/2 Vm squared over R, or 1/2 Im squared times R, multiplied by cosine of twice omega t plus theta v, or cosine twice omega t, plus twice theta v, or plus twice theta I, respectively, right? So I've given you relationships for the instantaneous power depending on only knowing the voltage or only knowing the current, right? As long as we know what the magnitude of the voltage drop is and the phase angle of the voltage is, or the magnitude of the current and the phase angle of the current, we're good to go. So we can tie this relationship directly back to our phasor circuit analysis. The only things we effectively get to solve the problems in the frequency domain and then pick apart the constituent bits of those phasor relationships to get our results in the time domain, which is exactly what we were doing with our steady state sinusoidal analysis. So do these representations for the resistor power make sense? All right, so let's think about it real quick. Like intuitively, sure, probably makes sense, or I wouldn't have told you. But if we were to look at the power absorbed by a resistor graphically, what we would observe is something that looks like this. So I'm going to start at its peak value. Which will just be Vm squared over R, or identically Im squared times R. So exactly half of the time it would be above 1/2 Vm squared over R, having a peak value of Vm squared over R, and exactly half of the time it would be below. But we should observe that when our power waveform goes on its negative half cycle, so when it's decreasing, it never actually crosses the horizontal axis. And it can't, because a resistor is incapable of storing power. All it can do is convert energy into heat, right? It can never store anything, does not have any physical process by which to do that. So this seems fairly straightforward. Our average power is simply the DC portion of our two time varying waveforms. So we could express this as 1/2 Vm squared over R, or alternatively 1/2 Im squared times R. So the DC portion of the waveform is the average power, just like it was previously. That's always going to be the case, right? Now let's talk about capacitors. Take that back. Let's talk about inductors, or inductors. So let's say that we have an inductor having a value of L, current I of t is flowing in, and a voltage V of t is appearing across the inductor terminals. Um, So just as a quick aside, and this mainly is because I can't always remember off the top of my head if it's plus or minus 90 degrees. We know that V phasor is equal to j omega L times I phasor in one of these guys, right? That's just Ohm's law using the impedance of an inductor. So we can see from this that the phase angle of the voltage is going to be the phase angle of the current plus 90 degrees. The magnitude of the voltage Vm is going to be omega L times the magnitude of the current, and therefore the magnitude of the current is going to be the magnitude of the voltage divided by omega L. And now we can use these relationships to determine the instantaneous power as a function of only the voltage quantities and a function of only the current quantities, just like we did for a resistor. So power absorbed by an inductor as a function of time is going to look like 1/2 so Vm times Im, that would be Vm squared over omega L. Or Im squared times omega L. So omega L Im squared. Then we are going to have cosine theta V minus theta I. So theta V minus theta I is going to be the cosine of negative 90 degrees, right? Because we'd have, actually cosine of positive 90 degrees, right? Because, sorry, let me think how to put this. Yeah, so we would have theta I plus 90 degrees minus theta I gives us cosine of positive 90 degrees. Yeah. So what's the cosine of positive 90 degrees? 0. So that means that our DC term all washes out to 0. Okay. So then we're going to have our twice frequency term. So that's twice omega t. And now I'm going to have theta V plus theta I, right? So that's going to be plus twice theta V minus 90 degrees for our voltage representation, and cosine of twice omega t plus twice theta I plus 90 degrees for our current only representation. Our average power by inspection is 0, which leads me to my statement that I said before. Whenever we have an inductor, exactly half of the time it will be absorbing power, and exactly half of the time it'll be supplying power back into the system. When we talk about complex power and all that kind of good stuff, I think next Monday, the fact that inductors and capacitors both behave that way will be kind of a sticking point on why complex power exists and how we design for that and all that kind of good stuff. So we will revisit that in a lot of detail in a little bit. Fairly obviously, I hope graphically PL of t should look something like this, where I'm playing fast and loose with the phase angles here. So again, exactly half of the time it's above, the other half of the time it's below the horizontal axis, giving us, again, an average power of 0. So for capacitors, where let's say that we have a capacitor C into which a current I of t is flowing and a voltage V of t is present across its terminals, we know that phasor current I is equal to J omega C times phasor voltage V, which tells us that theta I is equal to theta V plus 90 degrees. We can also see that Vm is going to be Im over omega C, and Im is going to be equal to omega C times Vm. So the instantaneous power absorbed by a capacitor is going to be 1/2 times the product of Vm and Im. So expressed in terms of the voltages, that's going to be omega C Vm squared. And expressed in terms of the magnitude of the current, that's going to be Im squared divided by omega C. Then we have cosine of theta V minus theta I. So that's going to be theta V minus 90 degrees. So that's the cosine of negative 90 degrees, which is also 0. So we know that our average power is now 0. Then we're going to have our double angle portion. So cosine twice omega t plus twice theta V plus 90 degrees, and cosine twice omega t plus twice theta I minus 90 degrees. Again, the average is equal to 0, and I'm not going to bother drawing a graph for this one because it's going to look identical to what we saw with the inductor. Exactly half the time the capacitor is absorbing power, and the other half of the time the capacitor is supplying power. Just shot myself in the face with water. All right, so instantaneous power and average power. Fairly straightforward, other than that pesky trig identity. And then we've gone through and we've used our frequency domain relationships to be able to express the instantaneous power and average power in terms of our phasor quantity, so that we can still do all of our circuit analysis in the frequency domain, where things are, well, I would say nice and easy, but they're definitely easier than doing things in the time domain. Any questions on this material? Roughly, it's pretty much all review from circuits 1, or it should be, depending on who taught you circuits 1. All right, well, I was not aware of that.
He doesn't like jokes. He goes over the formulas, and then he's like, watch our ground videos next class. Right.
Was that Harbor or Reese?
No, that's Reese.
All right, well, I gotta make better videos because I don't, Davis understands all the stuff that I was trying to go through. Lou may not. Yeah, I'll have to make better videos. I'm sorry for you guys having to suffer through that.
I don't know. I didn't necessarily watch it because I felt like his lectures got just
Right. Yeah, good.
I watched the first couple of them and I was like, wait, we're just watching it and then learning it again and then doing problems.
Yeah, that's, I would definitely agree that learning it twice would be a waste of time. All right, so let's talk about something new. that is going to be couched with something old. All right. So way back in circuits 1, when we were looking at DC circuits, we learned about the maximum power transfer theorem, right? That was part of the lecture on source transformations and all that kind of stuff. Okay. So today we're going to talk about maximum average power So as a quick review, in a DC circuit, where we can represent any two-terminal linear DC circuit by its Thevenin equivalent, which is what I'm doing here. So we have a practical voltage source being formed by a Thevenin equivalent voltage and a Thevenin equivalent resistance in series. If we load that network with some resistor, RL, we could observe a voltage drop, VL, across our resistor and a current, IL, flowing through our resistor, where VL is simply VTH multiplied by RL over RTH plus RL, using voltage division, nothing wild or crazy there. And we could say that IL is simply VTH divided by RTH plus RL. The power absorbed by our load resistor is then VL times IL, which is just going to be VTH squared times RL divided by RTH plus RL quantity squared. What we did in circuits 1 is we took the derivative of this expression for our power with respect to that load resistance RL and found out what value of RL caused the maximum amount of power transfer to occur. Do either of you guys remember what value that is? Yeah, when RL is exactly equal to RTH. So let me just write that down real quick. Max power transfer occurs when RL is exactly equal to RTH. That's perfectly correct. We are going to be applying the same basic process, but using impedances now. All right. So for a steady state sinusoidal circuit, where we have some phasor Thevenin voltage connected to some generic Thevenin impedance. So not the foggiest, whether it's resistive, capacitive, inductive, or some combination thereof. And we load our circuit with some generic impedance ZL. We could observe a phasor voltage VL across our load impedance and a phasor current IL flowing through our load impedance. So the average power absorbed by this generic load impedance should be what? Any thoughts? We just talked about average power for a generic circuit element like 20 minutes ago. You're putting too much thought into this. Literally regurgitate the equation I gave you earlier. 1/2 the magnitude of the voltage. So the magnitude of VL, right, times the magnitude of the current, times the cosine of theta VL minus theta IL, right? That has to be our average power. We have proved it. Okay. So what we're going to do now is we're going to spend some time figuring out what the magnitude of VL is in our system and how it relates to our Thevenin voltage and our Thevenin impedance. Similarly, how the magnitude of the current IL relates to our Thevenin voltage, Thevenin impedance. And then also how the cosine of theta VL minus theta IL relates to the our Thevenin voltage and Thevenin impedance. So let's start with our Thevenin, let's start with our load voltage VL. We can figure out what that guy is just using voltage division, exactly like we did in the DC circuit, right? So we know that it should be our Thevenin voltage, phasor voltage VTH times our impedance ZL divided by ZTH plus ZL. Seem reasonable? All right. So what I'm going to do now is I'm going to express those impedances in their rectangular form. So they'll have a real part, which is the resistance, and an imaginary part, which is their reactance. So in my denominator here, that's going to look like RTH plus JXTH plus RL plus JXL. And in my denominator, still have my Thevenin voltage phasor. And then I'll just have RL plus JXL. And what I can do now is I can effectively just group all my real parts together and all my imaginary parts together, which is going to leave me with a denominator of RTH plus RL plus J XTH plus XL. And my numerator is going to be VTH phasor times RL plus J XL. So if I want to take the magnitude of this guy, we hopefully have enough experience with complex numbers that what I'm about to tell you will make sense, okay? So should look like RTH plus RL quantity squared plus XTH plus XL quantity squared. That whole thing square rooted. So that is just the square root of the real part squared plus the imaginary part squared, which is by definition the magnitude of the complex number. And then in our numerator, we'll have the magnitude of the Thevenin voltage multiplied by the magnitude of just that load impedance. So that would be RL squared plus XL squared to the 1/2 power. Let me move that down a little bit. It's running into stuff and I don't like it. All right. So we have that guy figured out. We can follow the same process to determine our current. So using Ohm's law, it should be VTH over VTH plus ZL, which is then going to be RTH plus JXTH plus RL plus JXL in my denominator, and just a lonely VTH up here on top. And then grouping like terms, we'll have RTH plus RL plus JXTH plus XL. And so the magnitude of this guy, oh, excuse me, I shouldn't have the absolute value signs around this guy yet. So our magnitude, IL, is just going to be effectively the magnitude of VTH divided by that exact same denominator from earlier. So the magnitude of VTH divided by RTH plus RL quantity squared, XTH plus XL quantity squared, this whole thing square rooted. And so we have figured out this guy. The cosine term, so cosine theta VL minus theta IL, is a little bit difficult. So if I plotted, and here I'm making an assumption that does not remotely need to be true for this to work, but I'm going to make an assumption that my load impedance ZL is both resistive and inductive. So if I plotted my impedance on the complex plane, so this would be ZL. This angle formed right here, theta ZL, is by definition theta VL minus theta IL, right? If you don't understand that, which is perfectly reasonable, we know that the definition of impedance Z is V phasor over I phasor, which would be VM over IM with an angle, theta V minus theta I. Okay. So the projection of my impedance onto the real axis gives me my resistance RL, and the projection of my impedance onto the imaginary axis gives me my reactance XL, right? So based on this, what can I say about what the cosine of theta V minus theta I has to be? Cosine, remember from your high school trig class, is the adjacent divided by the hypotenuse, right? So that would be RL divided by the magnitude. So cosine theta VL minus theta IL is going to look like RL divided by RL squared. Sorry, that's not a plus sign. plus XL squared to the 1/2 power. We're taking the square root of that denominator. So if I substitute all three of those relationships in to my average power equation, what I find is that I will have 1/2 times, so this is going to get big and ugly, RTH plus RL squared plus XTH plus XL squared 1/2 power here, magnitude of VTH times RL squared plus XL squared to the 1/2 power, close bracket. So I've just substituted in the magnitude of my load voltage. Now I'm going to substitute in the relationship we got for the magnitude of my load current. RTH plus RL squared plus XTH plus XL squared, close my brackets, to the 1/2 power. Up here, we'll just have the magnitude of V Thevenin. And now I need to substitute in my cosine theta V minus theta I term, which is just going to be RL divided by RL squared plus XL squared to the 1/2 power. So what I can see is that I have this term in the numerator being canceled by this term in the denominator, which leaves me with I can also see I have this term in the numerator that's the square root of that big ugly thing multiplied by that exact same thing. So I'm just getting rid of the square root. So my denominator is going to look like RTH plus RL squared plus XTH plus XL squared. My numerator is going to be the magnitude of my Thevenin voltage squared times RL. So we've gotten significantly closer to getting an answer, but it may not be obvious yet. So let me ask you guys a question. Does having any reactance in this system make the average power larger or smaller? It absolutely, right? So the reactance is the X terms there, right? So if XTH plus XL, yeah, it's in the denominator, right? So it doesn't matter whether that combination is positive or negative. If it is non-zero, our average power is being reduced by definition. So we can use that to our advantage, okay? We know then that in order for maximum average power transfer to occur, at a minimum, XL needs to be exactly equal to negative XTH, right? We need to cancel out all of that reactance. So XL must equal negative XTH for max power transfer. So we have one piece of the puzzle, all right? So under that condition where we are letting XL equal to negative XTH so that our reactance term goes to zero, what we're left with, I'm going to call this P average prime for the sake of argument, is going to be 1/2 times the magnitude of our Thevenin voltage squared times RL divided by RTH plus RL quantity squared. So how do we figure out what value of RL causes maximum power transfer to occur for this expression? Again, too much effort. Let's so look at this expression right here. Get a good picture of it in your mind's eye. And now let's look at this expression up here that we maximized before. It's the same damn thing, except multiplied by a factor of 1/2. So we're not going to do any math because we already know what the answer is. So from this guy, we know that maximum power transfer occurs when RL is exactly equal to RTH. So putting this together, we can say that maximum average power transfer occurs when XL is equal to RTH minus J XTH, which is simply, excuse me, that shouldn't be XL, that should be ZL. ZTH conjugate. And from this, we can easily derive the expression P average max is simply 1/2 times the magnitude of our Thevenin voltage squared times RTH over twice RTH quantity squared gives us 1/8 the magnitude of our Thevenin voltage squared divided by RTH. And if we wanted to, for the sake of argument, express it in terms of our Norton current, since sometimes it will be more convenient to represent a circuit with a Norton current than it is with a Thevenin voltage, this would be 1/8 times the magnitude of I Norton squared multiplied by our Thevenin resistance, right? So that Thevenin resistance there, just to be clear, represents only the real portion of our Thevenin impedance. All right, and then applying this is just like applying the maximum average or the maximum power transfer theorem that we did back in circuits 1. So I feel like going through examples is kind of redundant at this point. If you can express your circuit of interest as its Thevenin equivalent, you've done all the legwork to be able to determine the maximum average power transfer. All right, so that's all I had prepared for today. If you guys got any questions or anything?
When we did inductors in class, we talked about how half the time with the power and half the time the absorbing time.
Mm-hmm.
Is they're both in the same circuit and they're opposite, right? Because inductors are also
Right, so the current and voltage are gonna, in an inductor, let's see, Eli the Iceman. So in an inductor, the voltage leads the current, and in a capacitor, the current leads the voltage.
right.
Okay.
So when they're both absorbing and giving out power, they're offset, does that make it like, I'm just trying to see, based on the
So,
graph.
so if you had a system that contained only a capacitor and only an inductor, no resistance whatsoever, you're asking what would happen.
Right.
So it depends, right? Because so you're going to have some inductive reactance and some capacitive reactance that you can combine together. So, right? So it's just literally combining the impedances. And then if it's more inductive than capacitive, it's going to behave like an inductor. And if it's more capacitive than inductive, it's just going to behave like a capacitor, because you can combine those two impedances together to get a single equivalent impedance, which will be purely imaginary, but it'll either have a positive sign, meaning it's inductive, or a negative sign, meaning it's capacitive. LC tanks, which is what that kind of thing is called, are used a lot in oscillator circuits explicitly. That is how, like if we went back to our transient analysis stuff that we did for second order circuits and we didn't have a resistor, what we would find is that we would always have an underdamped system where it would oscillate forever. Effectively, alpha would be 0, and so it would never decay. That will never be perfectly true because the inductor itself will always have some small amount of resistance, as will the capacitor. But a reverb circuit for a guitar effects unit is literally that. It's just an LC tank that just makes it ring in perpetuity. Old school reverb circuits, though, are not done using inductors and capacitors. It's actually a spring. So that's why they're called spring reverbs. But yeah. So that is how you convert a DC signal into just a ringing oscillatory tone. Or one way you can convert a DC signal into a ringing oscillatory tone.
So why does in transient analysis, why do we have a sinusoidal response even though it's a DC signal, right?
Right, so it's got that sinusoid, so it's a sinusoid imposed on top of a exponentially decaying.
Yeah, why is it a sinusoid? Right? In a DC circuit, there's no
sinusoid. So a better question might be, why is it an exponential? So it's a DC circuit, right? We're removing the DC signal from it. So why is there an exponential? The exponential is occurring because the voltage drop across the capacitor and the current flowing through the inductor cannot change abruptly, because to do so would cause an infinite transfer of energy. So they store energy and gradually release it back into the system. So another way of thinking about why a capacitor voltage can't change abruptly and why an inductor current can't change abruptly is because it takes time to transfer energy, right? Now, that sinusoidal signal that's being superimposed occurs only in underdamped systems, and it's behaving sinusoidally because the natural frequencies of the system are complex conjugates. So Euler's identity effectively tells us that when we have those complex conjugate natural frequencies, they're going to interfere in such a way as to look sinusoidal. Yeah, so math is a fantastic reason, yeah. And so that the frequency of the sinusoid omega d, you may recall, was related to the resonant frequency of the circuit omega naught and the Neper frequency, or the attenuation frequency of the circuit alpha. But so math also works.
Yeah.
Is our exam on this material still for next Tuesday in this line book?
No.
That was like way back at the beginning.
Yeah, so what we're going to talk about, let's see, today is Tuesday, right? Okay, so what we're going to talk about on Thursday is multi-frequency power which is going to be a bunch of tedious math. It's not anything different than what we did today, except that we're going to have to take into account that there's going to be several oscillation frequencies that are going to pop up. So multi-frequency, instantaneous, and average power. And then we are going to use that as a springboard to talk about effective values. So we'll cover multi-frequency power and effective values on Thursday. Then on Monday, we will cover complex power. I don't know if we'll get all the way through to power factor correction, just because I only have an hour and 15 minutes to talk about stuff. So theoretically, we really could have the exam on Tuesday if I went through the material quickly enough, but I don't want to. So I think next Thursday would be a better time so that we can spend a little bit more time, answer some questions and all that kind of good stuff. Well, actually, let me ask a different question, because what does the date of the test matter if it's take home?
Oh, I was wondering because I was gonna go home next week and I was like, for classes on Tuesday
Yeah.
instead of Thursday, or the other week. I was wondering this week.
Yeah, no, so I think we agreed for the first exam that all of the tests in this class will be take-home assignments. So that slightly changed my answer of, yeah, why can't I just put the test up on Tuesday and give you a week and a day to turn it in on Wednesday? Who cares? It's either I give it to you on Tuesday and you have until the following Wednesday to do it, or I give it to you on Thursday and you have until the following Friday to do it. What's the big deal? So the exam will be provided to you either on Monday, Tuesday, or Thursday, and it'll be due either the following Wednesday or the following Friday, just depending on when I feel like making the test, which I should do, and I legitimately had forgotten that I needed to make one. So thank you for the reminder. All right, so I'll post something when I make it and put it up. I'll post something on Moodle, and I think we're just going to have lectures during the day the test is assigned, because didn't we get behind because of something? So yeah. So for exam 2, whatever day I give that, we're just going to have the lecture as well, because it's a take-home test. So what does it matter? Okay. All right. So I think we have that sorted out. All right. I will see you guys on Thursday.